Hello, so today I'll be demonstrating contact angle hysteresis over a tilted surface. When a surface is tilted at an angle, the contact angles of a droplet on the surface change due to a shift in the inner line forces in the droplet. Normally, the contact angle of the droplet at the lower edge grows, while the contact angle at the upper edge decreases. The angle at the lower edge is known as the advancing contact angle, and the angle at the upper edge is known as the receding contact angle. When the droplet remains static on the incline, it is held up by a net interline force due to hysteresis that is also combating the force of gravity that pulls the droplet down the incline. The force balance equation of this situation can be shown here, which include the static contact angles and surface tension of the liquid, and the force of gravity at the incline. So for my experiment, I will pour a liquid droplet on a flat surface and incrementally raise the angle of inclination to observe how the drop behaves. I will be able to measure the angle of inclination and the static advanced and receded contact angles, along with the perimeter of the droplet for each step using measuring devices. I found that in preparation for this experiment, I actually had trouble accurately measuring the mass of the droplet. Each time I tried to, the mass measurement would be inconsistent or too small to measure with the scale I had available. So my goal is to use the data from this experiment and the force balance equation to determine the average mass of the droplet. So here are my materials. I have my laptop, some tape and rulers, and a laminated piece of paper, and I'll be using deionized water for my liquid droplet. So here, I tape the rulers to my paper and laptop, and also tape the paper onto the head of my laptop. My laptop is free to turn as such. So all I have to do now is pour a drop of my DI water onto the surface of the laminated paper, and I can open the laptop at any angle that I choose to record, and with some imaging software I can take a photo of the setup to measure the angle of inclination. Likewise, I can do this to measure the advanced and receded contact angles. And lastly, I can also measure the contact perimeter of the droplet by looking at the top of the droplet with the ruler at the side. I just trace a line along the ruler, so then I'm able to set a scale on my image, punch in the numbers, and get an amount of pixels per unit of measurement. And then the next step requires a more hands-on approach as I trace the perimeter around the droplet. It normally took me a lot of attempts to trace out, but once I did, I would be able to measure the length of the trace based off of the scale I set, which gives me the length of the perimeter. So I started off pouring the droplet on the flat surface, and then raised it up little by little, and based on my image analysis, determined the inclination angle for each step. However, I observed that the droplet began to slide down after it reached the last step at around 51.909 degrees. So I stopped the experiment and focused on analyzing the first 4 inclines. Based off of the images I took during each step, I found the other variables through the imaging software. After collecting the data, I used the force balance equation to determine the individual mass of the droplet for each step according to the variables I found. Overall, I found that they were adequately close enough to each other with a slight decrease in the mass as it went on, and so I found the average of the droplet, which was around 0.1455 grams. So in the end, I was able to determine the average mass of the droplet with very little deviation between each step. The decrease in the mass at the end may be explained by some evaporation of the water the further I went into the experiment. However, some errors may have taken place during the measurement of the data, A lot of work relied on me eyeing out the contact angles of the droplet for each step, and as I said earlier, it took a lot of tracing with my finger to outline the perimeter, and it may not be so accurate. So, quite a few technical errors may come from this experiment, and perhaps there were other forces that I didn't account for. But in the end, I was able to demonstrate the hysteresis of a droplet at an incline and examine the forces on the droplet. So, thank you for listening and have a good one.